Good. I'm all set. I don't know your name yet. Musaf is ready, right? I mean, is everybody else ready? If not, too bad, because it's really time for lecture 10, topics, oh, it's not topics in algorithmic data analysis. That shows how well I slept. Elements of machine learning, of course, lecture 10. We're going to be talking about clustering. And as you can see, we kind of diverged a little bit from the chapter numbering. So we're skipping a few things and mixing them up a little bit, because I think this order makes much more sense. Last week I already said that elements of machine learning is a little bit too much elements of supervised machine learning. And hence, well, we now have a small cluster of unsupervised stuff. And then we dive into the deeper end of supervised learning again. Let's get started. What is clustering? Suppose I give you some data, 2D plotted, right? Metric space. What do we see here? Is there any structure to this data? You, with the beanie, yes. No, there's no structure? Okay. Who wants, you want a challenge, not? There are two clusters, so either you're already looking at the PDFs or you have a very sharp eye. Indeed. I mean, either way it's correct. I mean, I'm sorry. I mean, no cookie for you. And for you, a virtual cookie. This group of points, they're quite densely packed, right? I mean, it's not completely, if I remove it again, it's not completely uniform, right? So saying that there's really nothing to be seen is a bit, if you say there is a lot to be seen, that would be a different question, right? These points have, well, relatively high similarity in between. They're quite close to one another. And if you define this group, then on the right-hand side, you see also a blob, right? That the lady in the back saw. That's this one. They also share well, they're similar. The distances are quite close, right? I mean, there's basically two circles here. And then we have some fluff in the middle. But essentially what we want to find these blobs that have a high similarity. And between the blobs, there should be low similarity. So if I take a point from the left blob, and I take a point from the right blob, they should be, in some notion, far away from each other, further away than within the clusters. At the moment that we can find clusters, like we did here, right, just by eyeballing it, we can also identify points that, well, do not belong to a cluster. For example, that one. It could be an outlier. This is not extreme outlier, but at this point, if we would drag it all the way to the floor here, then yeah, it would be very far from everything, right? It's somehow strange. We're not going to go that deeply into outlier analysis or anomaly detection. There's a number of different names for this. But perhaps the most important topic in machine learning, given that if you think about it, suppose that you're interested in winning a Nobel Prize, right? Let's project back 20, 30 years. Actually, a bit longer. The Nobel Prize was given out 20 years ago. But the discovery of the blue LED, that was one of those, I mean, like the discovery of penicillin. It was really completely random. In this particular case, there was a Japanese researcher, I forgot his name, sorry for that, who was looking through spectra of different materials, and they all looked very similar and boring. And there was one that's like, huh, it's weird. There's a weird peak somewhere. What does this do? And they started to investigate this, and actually this turned out to be a material that if you torture it enough, it starts to emit blue light, which was great because we already had red LEDs and green LEDs and RGB, as you know, together you have the whole full color palette. So thank you, Japanese researcher whose name I forgot, by finding by hand an outlier. Outliers, I mean, there's a number of cybersecurity students here, right? I mean, that's network intrusion, if you want to detect those. Perhaps all the intruders follow a certain pattern, but in general, there will be the weird ones out. You want to be able to detect those. There is an infinite array of, let's say, or an infinite broad market for the detection of outliers. And hence, it's such a pity that I don't have time to discuss it any further. We're going to be looking at inliers. We're going to find the clusters because they're also useful. How are those useful? User profiling. Sticking with the network behavior, right? I mean, that as an example. That is not a made-up one. This is something that actually is happening in practice, and for which, again, still a lot of new research is necessary. So, within some arbitrary company, right? I mean, let's call this company Max Planck, because I know that they had some issues with this a few years back. Individual users, they need access rights. You, for example, need computer A and B, right? And you need service C, and so on and so forth, right? But now, the one thing that you could do, you could take your system administrator, sit them down, and say, okay, think. what are the user profiles, right? Do we have user type 1, user type 2, user type 3? And then they have predefined this, and then any of us need to fit any of these roles. You can already see where this is going, right? One day after these roles have been defined, you come in like, yeah, but I'm both user 1 and 2, right? I mean, but actually of user 2, I don't really need this part. So you're then the outlier, so to speak. And so on and so forth. As a human, it's very difficult to determine what are now truly the usage profiles that are needed. But if you have data, and then finding the clusters in this data, which groups of users do we have, you can actually identify, well, what you otherwise would have to painstakingly write down and would make lots of errors. And if you do it data-driven, you get exactly how systems are used. If you throw in some biodata, gene profiling, you can identify cancers, cancer subtypes, because cancer is not one disease, there's many, many variants. How can we find them? Well, essentially by sequencing DNA of tumors, and then trying to group those DNAs of these tumors that are very similar, and then identifying somehow how many of such groups there are. And then, well, you've learned something, because now you can start to investigate, do these different groups really behave differently? Do we need different treatments for these groups? And so on and so forth. You've learned something. If you're interested in going from very big data to, well, manageable data sizes, you need data compression. On the right-hand side, there's a vision example at the top. Depending on how many clusters, how you basically assign your data points to which cluster, right? You could also see it a bit of segmentation at the bottom right. But if you now can identify how many meaningful groups of pixels you have in these pictures, going from 1 to 2 to 3 to 4 to more and more and more groups, you capture more and more detail, and somehow you can find the salient detail. You can do this not just for images, just images are nice to show, right? If I show it for arbitrary data, none of you would be impressed. I could just show percentages. But clustering is very useful. Visualization, perhaps we'll see later. What is clustering? Formally. Formally, we're given a set of objects, U, and we are given a distance metric. Does it need to be a metric? Yes. What is a metric again exactly? Come on, I'm not going to repeat everything for you. It takes 2 points, and it spits out a positive real-valued number, right? So basically, a distance at worst is 0 if the point is completely identical, and otherwise it's higher. Now, what we're asked to do in clustering is to group the objects into a certain number of clusters, right? Into clusters, such that the points that are assigned to the same cluster all have a very low distance, a low dissimilarity, or a high similarity. Those are the 3 terms that we use interchangeably all the time, so I will too, hopefully not to confuse you. And at the same time, you want points that are in different clusters to be, well, significantly different compared to the ones within a cluster. It's a very fuzzy definition, this, right? I mean, it makes sense intuitively, at least I hope so. I mean, I don't see anybody looking wide-eyed like, what the hell? But yeah, what is low? And the distance between points in the simplest should be low. That's not very well defined. The other one is large. I mean, what is low? What is large? I already slipped in. I mean, I was not even meaning to in this definition, but how many clusters? There's also, there's a lot of, which distance metric? We could say, okay, let's take a metric. Euclidean distance, sure, fine, but that is not always the right measure. I mean, certain features are more important than others. Differences in certain features are more important than others. So just a plain Euclidean distance, it's not going to give you a good time most of the time. What we just said. Now, one other thing that I haven't touched upon, so if we're now talking about clustering, so assigning points to a cluster, what does that mean? I can be very exclusive. I can say, for example, I cluster all of you into one cluster. The ones in the middle rows, from my viewpoint, mean, okay, you're cluster 2, and all the guys and the rest are the third cluster. The guys who are still standing are the outliers, right? Because they're different. And now they're part of cluster 3. I could be very exclusive. I could also say, well, actually, if I look at it from my perspective, there is sort of a group of people, including the gentleman there and I think one lady on the, for me, left-hand side of that. They form a cluster. You guys form a cluster. And you, so again, exclusive, but now not exclusive in terms of the banks, right? I could also say, well, I am now going to cluster everybody who's wearing a dark color. And but okay, but now you get to the point that if you have multiple colors, okay, well, let me see, your turn. Now I also know your name. You wear gray. So should you go into the people who wear really dark colors cluster, or in the people who wear really gray, white colors, right? Light colors. You're a bit in the middle, right? I mean, that's so perhaps we should assign you a bit to both. Could be, right? I mean, why not? There's no law against it. So then we are more towards a fuzzy clustering. You could also say, well, gray. Yeah? So you're wearing a light gray. So you know what? I'm going to assign you 80% to the light colored cluster and 20% to the dark colored or the darker colored cluster. Right? So basically, if I flip a coin, in 80% of the cases you go into the one, and 20% you go to the other, then we're in probabilistic clustering. These are three very similar, I mean, in the sense they're joined at the hip, but also very different definitions of how do we permit points to be part of a cluster, yes or no? And they lead to completely different results, completely different methods, and so on and so forth. For the remainder of the lecture, I'm going to be focusing on exclusive assignments, because that's the easiest and the clearest, right? But all the methods that I'll discuss can relatively easily be lifted up to the other types. Number of clusters that I did say already, a little slip. This number of clusters could be predefined. Find me 3 clusters, find me 5 clusters. Or it could not be defined. It would be like, okay, well, find me the right number of clusters. And as you correctly imagine, finding the correct number of clusters is a much harder task than find me k clusters, right? So you guess with which task we'll start, indeed, with the let's find k clusters. We're going to be starting with an algorithm that every machine learner loves to hate. So I don't know if the gentleman who asked me last week, what is the ultimate algorithm, right? If they are here, but, I don't think it was him, but I mean, okay, maybe it was, maybe it was. Wait, were you the guy who asked what is the ultimate algorithm? Were you last week the guy who asked what is the ultimate? No? Okay, I see some, okay, no, never mind. It would have been like speaking of the devil, right? Good. So you're not the devil. That's good for you. That's good for you and good for us. We're going to be talking about an algorithm that is sort of the first attempt that you do when you cluster. And it's remarkably difficult to beat unless you feed in a lot of knowledge into another algorithm. You make a very dedicated algorithm. It's a bit like linear regression. The reason why we teach linear regression and logistic regression, and I have something to say about that in a few lectures again, those are these basic workhorses that they just do remarkably well, and beating them really consistently is ridiculously difficult. For clustering, it's called k-means clustering. It's an iterative method where we assign the points that we have, the u points, into k clusters, and then iteratively we're going to reassign points such that they become more and more cluster-like. Right? We start with a random assignment. And at the end, well, at one moment it converges, and that's the result. That's in a nutshell what we do. We find disjoint clusters. So essentially, what we have is that here, cluster 1, if we take the union with cluster 2 all the way to cluster k, I could have had here, well, just u. Right now I just enumerate the data points, 1 till n, same thing. The intersection between these clusters are 0, yeah, otherwise it's not disjoint. No, okay, that's basically saying the same thing 3 times. Now what we want, following from the intuition that I started with, we want to have that per cluster, for each CI, basically the spread of the points within the cluster should be small, right? The distances between all the pairs of points within this cluster should be small. It's one way to think about it. And the distances between the points in different clusters should be high, naturally. So the within cluster variation, which here we write as the W for a specific cluster C, I, CK, whatever. So we want to minimize the sum of those. Good. There are perhaps not infinitely many, well, unless you go for trivial results, but there are incredibly many ways to define what is now this within cluster variance. The most natural way to do it, and that's what we follow for now, is to assume that we live in a metric space, Euclidean space, right? And that, so just easy peasy. And what we can then do, we have a definition, and this is the within cluster. we're going to normalize by the size of the cluster, so how many points are assigned. For every pair of points within the cluster, for each of the dimensions, we basically take the squared distance between them. Then, yes, exactly. Yes, yeah, exactly. So basically, if think of the blobs that we had, right? I mean, that's C1 is perhaps the left-hand blob, right? I mean, and what we now do for every pair of points, of every I and I prime, we now, for every feature, we say, okay, what is now the square distance, right? Hence Euclidean distance. That's what we have here, right? And obviously, if I do this one by one for every dimension, that's what this sum is. This is basically the stupid way to write it. I'll be back with you in a second. You could also just take, well, just the squared, the norm between those observations as entire vectors, right? Same thing. That depends on how you write things down. This is we, and by we I mean machine learners in general. I mean that perhaps we're not. Well, perhaps it looks like we just always just make a mess and invent new notations, right? But we often slightly abuse notation. That's literal wording you will see in infinitely many machine learning papers to do exactly these types of things. So in a way, you're correct. But so I and J, you could see them already as the xi's, but now you want to identify something within that becomes very cumbersome to write. So let's just do the index. This is a bit where, well, you have to read machine learning papers, and therewith also the book. The book is reasonably consistent, but also the assignments with a bit of, well, common sense, right? But the moment you would do this too, let's say too mathematically clean, the whole thing becomes unreadable. But you have a fair point. Anyway, just squared distance between two vectors, right? And we do this for every pair of points. Now, suppose that we now want to minimize the sum of these distances, right, over all the clusters that we have. So we want to find really the optimal assignment into k clusters. That is a very difficult problem on many accounts. So how many partitions are there? This is the Bell number, Bn. It's super exponential. It's very nasty. So there's essentially no way, unless you just literally have a handful of points, to enumerate every possible assignment and compute what these scores are and then take the best one. So the exact solution to k-means, forget about it, right? Not going to happen, not going to happen. So another tricky thing is that k, already alluded to the previous, choosing k the correct way or the correct value, very difficult. Essentially impossible. We'll go there in, well, sometime. Actually, well, in the next slide I have an example, but then later we see it again. So let me just show you what would be the result of k-means, and then I can start to explain how we actually achieve those things. So here we have some data, and if I would now to ask, well, the lady in the back, I mean, how many clusters are there, right? I mean, or what are the clusters? If there are two, then probably you would say, well, even without the colors, right? One at the top, one at the bottom, right? Yeah, see, that's very good, very good. Now, I could also ask, if we have the same data, and I ask you to find 3 clusters for me. Where would these clusters be? Like this? Okay, very good, very good, very good. Okay, good. That's you're too good at this game. So I'm now going to ask somebody else. If you would now ask, okay, I want 4 clusters. You. What would you do? Yep, yep, indeed, indeed. Anybody else an idea? So it's not wrong. It's not wrong, right? That, the middle section, that one I prepared. So, but what you were saying is absolutely correct. It's equally correct, right? Perhaps this is the optimal assignment, but I just said finding the optimal assignment for a non-trivial number of points, we don't never know, right? So I don't know if this is now correct. I don't think so. But, what I want to illustrate here is that effectively there is not a correct answer, or it is not so clear what is the correct answer. Maybe there are truly 4 clusters, and then maybe that one is the correct assignment, and maybe yours, also very sensible. Maybe there are only 2 clusters. Well, then it's reasonably easy, right? If you would slice it differently, then it would be weird. But it's not just difficult to identify the number of clusters. It's like, well, what is a correct clustering? Clustering is a very fuzzy notion. What is similar, what is not? Good. Let's go now to the algorithm on how you can find k-means clusterings. It's called Lloyd's algorithm, very classic. If I recall correctly, it's from the, I think, 67 or something. It's ancient, and this is why we hate it so much, right? I mean, you kind of like to improve over stuff, but people still use k-means in practice. That's a very slight improvement the last few years, but still. Because we already accept that we can't find the optimal solution, well, we could go just for an arbitrary starting point, right? I mean, really arbitrary in the sense it's defined and we always use this. Or we can say, screw it, we just use randomization. And that's what we do in Lloyd's algorithm. We start with a completely random assignment of the data to the k clusters. So we now have basically a mess. We're just like a bunch of confetti that we threw in the air, right? Now, that doesn't really create a problem, because what we can do for each of the clusters, we can compute all these distances. And, well, we can then start to see, okay, if we now move a point from here to there, from there to here, do these distances, do they shrink? Well, that's essentially what we do. That's essentially what we do. But what we rather do instead, for each cluster, we compute its centroid. Because, let me see. I'll quickly go here, and then I go back to the other slide. We can interpret how we defined the intercluster variances. We can interpret it slightly differently. We can rewrite it slightly. So the overall objective is what we have here. But if we now, in this rewritten formulation, we have here the data point, and this is the mean vector for that particular cluster. Whether you now compute like between every pair or compared to a mean, well, what is the difference? Yeah, if you do it with the mean, then you essentially have twice the distance, right? Otherwise, that's essentially what it comes down to. So we don't have to always compute all the pairwise distances. We should just compute for a cluster its mean, and then for each of the data points, the distances to the mean. And then we're good. Then we're happy. Still, the rest holds. We'll perhaps go there later again. This is going one slide back. So for each cluster, we compute the mean. We call this thing the centroid. Mind you, the centroid is a data point that could exist, but may not exist, right? It's not necessarily in the data. It's really just the average. It's important to keep in mind. Now, after we have computed these centroids, for all the data points in the data set, we're now going to assign it to the closest centroid, right? We basically number all the centroids from 1 up to k, and then we assign points, and then we have a new clustering. Well, repeat until you're bored. When are you bored? When it converged. Does it converge? Whenever there's some minimization or maximization, you should always ask yourself, does it converge? In this particular case, I'm not going to go through all the details. It's reasonably straightforward. But yes, essentially, in every step, what we do, we are always minimizing. There is no possibility of increasing the variances. Given clustering, compute centroids, we reassign things. The only way to make the distances larger is by reassigning in such a way that we don't minimize. So in the worst case, nothing changes with the reassignment. Well, that's called convergence, right? So in the reassignment step, we minimize. Then we compute the centroids. Well, if by a reassignment we minimize, then we get a better centroid. And it may be that points flip-flop a few times between one cluster and the other, right? While it sort of agglomerates different points, but at one moment it stabilizes. Long story short, we choose the centroids to minimize, we choose the cluster assignments to minimize, and in the end, it converges. This is back to the slightly more in-depth slide. So we were roughly here. The joint optimization, difficult, but we can break it down to its parts like we just saw. This alternating optimization or basically this idea of taking a complex problem, find all the clusters that minimize in one go, right? You encounter these types of problems very, very often in machine learning, these optimization problems. And sometimes you can show that this is NP hard to optimize or otherwise, hairy, right, in a way that you don't like. Sometimes you can't show it. It's just like if you run it, then it sucks. So very often we break it into two parts. And this very often works remarkably well. It's one of the reasons why k-means work so well and why we hate it / love it so much. But this is a very general strategy. You haven't seen this much within this lecture series, but you will see it elsewhere. So we are not going to be talking about EM, expectation maximization. This is essentially the probabilistic version of k-means. This is how you can interpret it. The Gaussian mixture models. Gaussian mixture models are a special case of EM. These are very powerful model classes that people very often use. Also impossible to optimize jointly. Just break it into two parts, to the one to the other, flippity flop, done. So the strategy, that is perhaps the most important thing from this slide to keep in mind. A good minimization strategy. Good. Let's see if Lloyd's algorithm works or how it works. The algorithm again on the left, just reorganize things a little bit. I have some data, we recognize it, and we start with a random initialization. So that's step one. And I did not make, I think I see three. I think we have three clusters here, or at least three colors. So that would be the cluster assignment. So what we now do is per cluster, we compute the centroid. There we are. As you can see, these centroids they overlap massively, right? They're very simple, like you would expect, right? That's if we would have an infinite, if we the entire population, then they would all completely coincide, and we would be screwed, right? So this is also an algorithm that works better in practice than in theory. It's a bit weird, right? But really, you need a limited sample, otherwise it starts to go haywire. Good. But now we have these centroids, and as long as they're not exactly the same, we're good. Because this cluster here, so this centroid over here, this blob over here, this is closer to all points on this side. This one over here, very much overlapping, but it is closer to all these points over here. And the same thing here, a little bit to the right, it's closer to all of those. So if we now start to assign points to the closest centroid, what we do get is this. Well, that looks already much better, right? And quite close to the clustering we saw earlier. But we're not done yet. First, we have to now, for the new assignment, compute or recompute the centroids. There we are. Then it may be that some points are now, that used to be green, are now closer to the pink one, and so on and so forth, right? Probably there's going to be a battle between the top and the bottom half. No, yep. After 10 iterations, it looks like this. 10 is here really just in this particular case. Often, in my experience, often 5 iterations is already enough. But your mileage may vary, as they say, right? It really depends on your data and how lucky you were or unlucky you were with the initial assignment. Because you can also see, or intuitively see, that if the random assignment was slightly different and, well, that these 3 points were slightly rotated, we would have ended up with a very different clustering. It's a randomized algorithm after all. So we could have ended up with this one, or that one, or many, many different ones. Which is now the best one? Well, by definition, the one that minimizes our score, right? So there is one here, that's the one here at the end, I think. What is it? Look at here. Actually, no, here, these all have the same score, and also these are all just permutations of each other. These are just identical, subject to label change, right? And that, okay. Doesn't necessarily have to be, right? You could have 2 clusterings that have the same score but are really qualitatively different. Effectively, what you do with k-means, you run it multiple times, and you take that clustering with the best score, and that one, or maybe those, right? So if you have a few competing ones with a score very close to it, those you show to your domain expert, or you analyze yourself in more detail. That's how you roll, right? That's good. Let me take a sip. Although on paper, assigning points completely randomly initially, it's fine. We've seen that it works, right? It has a few downsides. I'm not after the fact that, well, you have a random result. You need to run it multiple times. That is something we can't really get away with, right? But can you come up with some problems that the completely random assignment may create? And then the next question is going to be, okay, how could we possibly fix that? Let's first see if we can find the right problems. Does anybody have an idea? What is kind of stupid or what kind of wasteful by completely randomly assigning points to clusters in the first iteration? Yep. Yes. Exactly. If we already know something about the distribution of our data, then why should we let that? That's correct. That's correct. But, in k-means, this is relatively difficult to include. So the only way you can meaningfully include this, like without basically painting your method completely into the corner, right? That would be by adapting the distance measure. By using a distance measure that groups those points that we believe are more similar, more closely to it, and okay, then that works. Then that works, right? That's, okay, no, I'm getting a warning here, but everything is fine. So, and the painting into a corner, why is that? Well, we could say we already put those points together in a cluster, but yeah, then we kind of take away the liberty of the algorithm to explore, right? It's really in the exploitation phase, right? Exploration trade-off. So it might not find a truly good solution because we steered it too much into. No, this is an approach feeding in extra knowledge that is better suited for EM or GMMs. For k-means, it's a bit more difficult. Is there another downside? Or in a way, it is actually in your answer already embedded, but I mean, perhaps we can phrase it slightly different. Yep. You can consider this outliers as single clusters. Yeah, absolutely. In fact, let's just a small aside. Let's think about the downsides of k-means, right? Or what are the pitfalls? What is it sensitive to? You mentioned outliers, right? I mean, we already discussed outliers in terms of regression, right? Leverage points and outliers and stuff like this, right? How good or bad is an outlier for k-means? Suppose that we have this data, but I also have a point here right on the floor, right? I mean, that, is that a good or a bad thing for k-means? Or does it say shrug, right? A good thing is never a good thing, but doesn't it care, or does it care, well, way too much? What do you think? Exactly. If there's an outlier, that shifts the centroids really massively, right? So this is clearly a problem. We need to solve this on one of the next slides. But, okay, so let's steer to the point. You mentioned that if we have background knowledge, we can save many iterations, right? Well, what if we don't have background knowledge, but we do want to save iterations? That sounds like something that we would like, right? And by doing something, assigning completely randomly, yeah, we need lots of iterations to sort of escape from this initial assignment. Wouldn't it be much smarter if we somehow assign the centroids, and hence the clusters to the relatively far away from each other, rather than all clumped together? That sounds like a reasonable thought, right? That is called k-means plus plus. Proposed not, yeah, the naming, I mean, that computer scientists and creativity, right? I mean, that's, what does k-means plus plus do? It's not part of the lecture and hence the exam. Essentially, I would ask any of you, okay, well, close your eyes, throw a dart to the screen, right? And the point closest to where your dart landed, that's going to be my first centroid, right? That's, okay, good. This is the starting point. What we now do, I compute all the distances for all the points to that centroid, right, to where your dart landed. And now I'm going to ask you to throw another dart, but then a special dart that chooses a point proportionally for how far away it is from the first centroid. So essentially, you choose you have a very high probability, if you landed first here, to not land here, but being a bit further away, and specifically where lots of other points are. lots of points far away, well, you have a high probability of landing here, whereas the lots of points here, yeah, they very low probability. So you throw your dart and it lands over here, right? Very good. Now we redo this entire game. We compute now the distances of all points to the two, right now the two centroids that we have. We do the same thing. We have a new, effectively, probability distribution over data points for the probability to become a new centroid. You throw your dart again, and that would be now in the third class. So basically, we maximize, although randomly, our probability of choosing a centroid within the dense areas in the data that are far away from, basically hits really the centers of a cluster. Yes? It was just in this example. So the what you generally do have is that it in this first iteration, it does this very big assignment, but it very often then gets kind of stuck in the fine-tuning. And by choosing these centroids a bit more smartly, it can immediately go to a fine-tuning where there is not so much competition anymore, because you've found your centroids already in areas with relatively many points far away from other points. Ben? Both. So we do it randomly. So the first step is really choose your favorite point. That's basically what it comes down to, right? Because we don't have any, well, zeroth centroid, right? And that, so it's really any point is equally likely to become a centroid here. But, perhaps with some smart techniques, you could say, okay, well, actually, I want to give a higher probability to those points that will have many neighbors close by, and also many neighbors far away, but that would be k-means plus 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 probably, or k-means sharp, or whatever, right? And that's .net. Good. Anyway, k-means plus plus, super simple idea. I believe this was proposed, I think it was 2005, at the top of my head. I may be off by a few years. Well, 2005 is some time ago, but at the same time, I mean, for such a simple idea that built on top of an algorithm that has already existed for essentially 40 years, what, right? But this happens a lot in machine learning land. There's all of a sudden a result that improves quite massively over something that is ancient. Good. So, long story short, for EML, for the exam and whatnot, use k-means, just do it the stupid way. If in practice you want to use k-means plus plus by all means, right? Now, quickly on how do we choose the number of clusters, right? This is a slide I actually should have included, perhaps partially the left-hand side in last week's lecture, where one of the questions was, how many principal components do we need to find, right? And that's, Ben, you had a question about this. And I spoke about the elbow rule, right? The elbow method. And like in cross-validation, you try to find the minimum within one standard variation, whatnot, right? That's standard deviation, sorry. So here on the right-hand side, you would have the average within cluster variation for number of clusters. And as you can see, this drops. Obviously, I mean, this keeps on dropping, right? I mean, that's all the way up till n data points. So, but looking at this, what is now the right number of clusters? Well, by a completely heuristic, so not really well-founded method called the elbow method, you basically find the elbow, and that would choose this point over here. Which, yeah, makes sense. Makes sense, right? I mean, these here don't really add so much. And yeah, well, there you are. For the principal components, you have the opposite, the amount of variance explained. So there it's essentially where, well, you also have an inflection point. So this is the point where you say, okay, well, now, jetzt reicht's. Good. Elbow method. This is what people do in practice. Is this the right way? Is this the best way? Hell no. But it works remarkably, well, sufficiently well in practice. Good. Let's continue. Oh, yeah. And I already showed it. I mean, that's, I could hide it again, but that's a bit. For those that read more quickly than the others, that would be at the advantage. In k-means, we use these centroids, right, which are defined as the mean value of a cluster, right? And that, We already, thanks to you, identified that this actually leads to a very brittle algorithm if there are outliers in the data. That's because an average, a mean, is a brittle, it's a non-robust statistic, right? And that if, let's say, I measure the heights of all of us here, right? And that's and for one of you, I placed a comma wrongly, right? And that's and then I compute the average. That's going to screw up everything massively, right? And that's so it's the mean you actually kind of want to avoid. It's just that within k-means, it's very convenient in the optimization. So you could have the thought like, okay, well, if you compute a mean, this is brittle, right? If you go now for, well, the medioid, so what is that point, the actual data point that splits the data best half-half, right? So what is the median salary, for example, rather than the mean salary? Can't we also do this in k-means? Well, if we do this, then we arrive at k-medioids. So essentially what we do is that we start with some assignment, and what we now do is we're not so much interested in computing the mean, the centroid really. What we're now interested in is to try to find that point that is most central, but that point that really exists. And this has, besides the robustness that it gives us, also an additional feature, you could say, because the medioid is an actual data point that we can look at, that makes sense. Whereas the mean can be arbitrarily wrong, right? It can combine certain values like, okay, yeah, this can never happen, right? This is not viable. Whereas the median always will. So hence people were very much in love with k-medioids for a little while, until they realized that the optimization, doing this, is, well, ridiculously hard. It's not just that the computation goes from linear to squared. The entire problem, the assignment problem, becomes NP hard if you want to do this properly. So yeah, in practice, k-medioids you kind of want to avoid. But sometimes you need, if you need really representatives, cluster representatives that are actual data points, yeah, there you are, right? Good. Yeah, let's take a short break, and then we're going to talk about hierarchical clustering. So I'm going to blank the screen, and let's reconvene in, well, let's say 10 past. Is this fair? Yeah? Good. 10 past. Okay, it's 10 past. Let's get started again. I now explained the one algorithm that machine learners, when it comes to clustering, love to hate. I'm now going to explain the other one. First one, k-means, it's randomized, right? And you recall from last week, I'm not a big fan of randomized algorithms if I can avoid them, right? Sometimes you can't. Sometimes, I mean, randomization is a great way to, on expectation, get good results. But running it, like everybody here will get a different result, right? I mean, if you have a sufficiently complex data set, none of our clusters are going to be the same, even if we all of us run it many times. I don't like that. I don't like that. So you can also rethink clustering then from a way that avoids random assignments, random initial assignments completely. And well, if I would have locked you into this room, it's okay, I'm not going to let you out until you come up with a reasonable algorithm that clusters points. I'm pretty certain, if I would repeat this experiment many times, that in many cases you would have come up with what we call hierarchical clustering. Hierarchical clustering is, so A, it's deterministic, B, it avoids, in a kind of sneaky way, having to choose the number of clusters, K. It's sneaky because effectively it finds a whole set of clusterings. It finds a clustering into 2 clusters, into 3 clusters, 4 clusters, all the way up to n clusters. That's essentially how it rolls. Hierarchical clustering, there's 2 variants, bottom-up, top-down, agglomerative, divisive. And essentially what we're going to be doing, and now I realize I don't like the ordering of the slides that I chose here. Mind you, by the way, that right before the lecture, I reordered some of the slides. So if you're now looking along in the PDF, you're like, okay, what are you doing? Yeah, I'm sorry. I thought that this order was better. And up till now, I was right. But here I was wrong, if I reordered those. Essentially, what we're going to be doing, looking at the picture to the right, we're going to find those two data points that are closest. Okay, and we now going to put them together, right? And that's for the time being. We're going to treat them as one cluster, right? So not really one data point, but one cluster. They're now clustered together. Next step, we're going to find those two. Actually, no, let me actually rephrase it. In the beginning, all points are their individual cluster, right? Singleton clusters. We now find those two clusters that are closest to each other. And we put them together. They're now one cluster, right? We merge them. Rinse and repeat. Keep on joining those two clusters that are closest until everything has been joined together. That's agglomerative hierarchical clustering for you. I will show it in an example slides a bit later. Well, if that is the one, we can also do the other way around. Let's join all points together, and let's now find that split into two clusters that maximizes the dissimilarity between these two clusters. And then keep on doing this. So I said we go from one big cluster until we have n clusters. Right. This is top-down or bottom-up versus top-down agglomerative clustering. Both methods produce dendrograms. What is a dendrogram? Dendrogram looks like this. It's a tree-like structure, it's dendro, where you show the clusters and the distances between clusters. What do we have here? These are the distances on the y-axis, and on the x-axis we have data points, right? So each of these bars are a data point. We currently can't really read the labels, but that doesn't really matter. And what we now do initially, let me try to find it. I think it's this one. I think this is the first merge in this cluster. We will see other examples later on, but all the way on the left, those are those two clusters in the initial stage, those two data points that were closest, and we're going to merge them together. How far apart were those clusters? Well, that is very simple. This is actually, I'm now a little bit unhappy with the fact that actually this distance here, right? So basically from the data point, which is that dot over here where I'm hovering over right now, so now you can see it again, and where this data point was maybe here, I don't know. But the distance to this area that I'm now going over and where they are joined, that was the distance between the two original clusters, right? So you can read off, hey, these two were merged together, and that created a distance within the cluster of this size. And we try to merge always those things that are closest. Good. And then, well, in the end, here at the top, we have merged everything together. Over here, right? If I cut over here, let's do it like this. I have clustered all those things together, and they have a similarity together of this. And here on the right-hand side, I've clustered those all together, and they have a similarity of that. So we already know that the left cluster is more similar than the right cluster, right? But if you want two clusters, here you are, right? Where should I draw the line if I want three clusters? It's not a trick question. Ben? Around 6. Okay, the example is more at 5, but okay, that's 6 I like personally better, but okay, that's same thing, same result. We could repeat this game over and over, right, all the way up till n, but as you see, right now we have one depiction where we simply group points together, or we split them perhaps divisively, but nobody does that in practice, and you get a beautiful depiction of which points are now, well, belong together or not. You liked outliers, right? Or maybe you hate them, I don't know. One of the two, you have an opinion about outliers. Now, without knowing all too much detail about hierarchical clustering, do you think that hierarchical clustering is more, similarly, or less sensitive to outliers than k-means? It's less sensitive, you say. Okay, why? It is correct. We're comparing always distances between clusters. So if there's one cluster that's really far away, it could be a singleton point, it could be 2 points, we don't really care, but it's really far away, we're not going to merge it with any of the others until, well, at the very, very end, right? Or very late in the game. Basically, when we're merging clusters that don't really want to be merged. That's the moment. So where do you think then an outlier, where would it be in this, so how would it look like? Yes, exactly. It would essentially be, well, so a branch here, let's say the distance here, floop, and then just all the way down, right? It's a point that no cluster wants it, right? I mean, that's it's sort of like, okay, I don't know what you're doing here. I mean, that's somebody got to come out wrong or whatnot. So hierarchical clustering is not only robust against outliers, right? Rather than brittle, it doesn't break apart that easily. It also allows you to spot outliers very easily. It also allows you here to spot if clusters are more or less similar. Let me go back to the two clusters. I kind of already gave the answer a minute and a half ago, but which of those two clusters is, let me call it, more compact? In the sense that the data points are more similar within the one cluster than the other. So which of the two is the more compact cluster, would you say? You. Yes. Yes. Identical? No. So which of those two clusters, the purple or so the left or the right one, the purple or green one, which is more compact? Purple. Yeah, does everybody agree? Yeah, me too, me too. Why? Hey, look, this is the similarity within that cluster. This is the similarity within that cluster, right? So also by looking at this dendrogram, so we now already decided, like, if I were to ask for 3 clusters, but just by looking at it, you can kind of see what are the reasonable choices. 2 or 3? I would say 3. 3 seems more sensible here than 4 or 5 or 1, right? But 2 or 3, 2 or 3. So we don't really need this elbow method. We quite directly see qualitatively which ones are more or less similar. Good. Let's see. Yeah, this is important. So the y-axis in a dendrogram is very interpretable. Those are the distances between clusters, right? But, how we define the distance between a cluster, it's a completely different matter, right? I mean, that may be very uninterpretable, but the distances are by themselves interpretable. Now, the x-axis, the order in which the data points are grouped, is essentially meaningless. This is really just, we chose those 2 clusters were closest under our definition of how close clusters are, right? If you compare the left and the right-hand side, I mean, points 3, 4, 1, 6, yeah, right? So that's 3, 4, 6, 1 would have been more sensible ordering. 3, 6, 1 maybe. You see what I mean? You see what I mean? But, oh, yeah, another one. But, good. Dendrograms can be visualized in many different ways. The standard way is here, like we have on the left, be it with a 0 axis or not. That, in many more fancy papers or papers that want to be fancy, they actually draw it like this circle thing, which I personally like. It's visually very appealing, and it conveys the same information, but the left one, the boring one, is a bit easier to read, right? I mean, that's even if the eye may not like it as much. But, good. Does a dendrogram or does a hierarchical clustering, does this always make sense? Not really, not really. But, if the data looks like we have on the right, so we have 3 nationalities, men and women, that's the split here. But this is essentially what the data looks like, right? And that's, so we have American men, American women, and so on and so forth. Then you kind of would like to cluster like that, right? That's, so in a way, if the data looks like this, k-means might be good, because k-means could find a blob for each of the cells, right? Hierarchical clustering is screwed. Because, yeah, you can either have the left or the right hierarchical clustering, and yeah, they're both kind of meaningless, because it just wants to combine things, and either you combine it first on the y-axis or first on the x-axis, and then you're completely stuck, right? There's not really a way of seeing it, the entire picture. So there are cases where hierarchical clustering just inherently makes less sense than k-means does, or other clustering techniques. How do you know whether it makes sense? By trying it out and seeing, looking into the cluster, doing cluster analysis. We just had a short discussion with Haya. I'm not going to go too much into detail there, but perhaps in one of the later lectures, I try to squeeze in some more modern approaches to what can you actually learn from a cluster. Right now, today, I don't have the time for that. Good. Agglomerative clustering, where we start with the singleton clusters and then, well, just merge them until we're done merging, is in general superior to divisive clustering. Although technically, if you write down all the full optimization problem is kind of the same, right? I mean, the space of solutions is the same. But in agglomerative clustering, you're somehow, it's a bit more permissible to make a small error. If you first merge 2 points together into a cluster that actually should have been merged much later, or much later, a bit later, that's not so much of a problem because in the end, we just group, we kind of fix it along the way. Whereas in divisive clustering, if we choose a split of the data into 2 halves, there's no way of recombining parts of those splits again, right? So we paint ourselves very quickly into a corner. And because we make this decision locally rather than globally, it is very easy to make a stupid mistake. So in general, we don't like divisive and we do like agglomerative clustering. Also from a computational perspective, divisive clustering is much more tricky because if I group all of you now together and say, okay, what is now the best way to split you into 2 halves? Essentially, you have to look at every possible way to split you into 2 halves, right? That's a lot. It's exponentially many. Whereas if I say, okay, well, all of you are now a singleton cluster, let's now see which 2 of you should be put together into 1 cluster. It's much easier because we just need to compute the distances pairwise, right? Which is essentially quadratic. There we are. So quadratic versus exponential. Good. Okay, well, the algorithm now already said a number of times. Each observation is a singleton cluster, compute pairwise dissimilarities, merge. Fuse the most similar clusters. Now, of course, after we have merged 2 points, we now need to compute the distances of all the other clusters to this new formed cluster. Because this may or may not be the same as the distances of the points within the cluster. It means that we need to talk about cluster similarities and dissimilarities. I would like to play a little game with you. That sounds a bit bad. Let's think about ways of how we can measure similarities between clusters. Does anybody have, and it should work both if the cluster is just 1 person, right, or a group of people, or 1 data point versus many data points. Ben, do you have an idea? Okay, yeah, so the different things was exactly what I was after. So yeah, so we look at the pairwise distances, right? But yeah, how do we compute those now exactly? And then we do different things to it. You said minimum and maximum, right? And that's let's go a little bit into the minimum first as an example, right? How would you? I don't have a slide to really illustrate it that well. How would you picture this? And when I mean you, any of you, right? And that's suppose I have a cluster here and have a cluster here, right? And you can imagine that there's like data points within, right? And that how would you, if we now go for minimum distance, how would you define the distance between these 2 clusters? It's not a trick question. I just want to put it visually. Yes. The mean? Okay, yeah. That is yet another method. I'm now interested in the minimum. Ben, or actually no, we already spoke too much. You. Say that again, sorry? Yes, the distance between my thumbs. Yeah, this is exactly why I was holding them like this. Exactly. So we find that point in this cluster that, so basically this is what Ben was saying earlier, we compute the distances between all the points here to all the points there and vice versa, but that should be metric, so that's then the same. And then we take the minimum of those. So this is this. Suppose that we're going to be doing this, right? This is called single linkage, if I'm not mistaken. The next slide will show it. But, what shape of clusters are we going to get if we join closest points, if we join thumbwise? Does this give a preference to the the shape of the clusters that our clustering algorithm is going to find. Yes? We get weird structures. What is a weird structure? Not a ball. No, exactly. If we want a ball, right? Everybody likes like balls, bounce, bounce, bounce. We want a ball. What measure should we use? So what is the distance between the two clusters? I can do this. We want a ball. Yes, you're all the way in the back. They have a name. They're called pinkies. Yes, exactly. The furthest fingers. You take the furthest points, because then you create very compact clusters, right? And if there's one point very far away, right? So let's say we have this cluster, right? It's just this, and we have one that is super, my pinky is then somewhere all the way over there, right? Super spread out. I would prefer this one because that keeps things compact. So the maximum distance creates very spherical types of clusters, and indeed the single language, the shortest distance, creates weird structures. Complete linkage, compact. Single linkage. Yeah. Yeah, so let me repeat the question. Why don't we just compute the centroid and then measure the distance to the centroid? Why? Why don't you answer it? Can you see a downside to this compared to the other two methods? How many steps of computation do we need? We need a bit more. In the end, oh yes, gentleman behind you. Why would we get overlapping data points? Okay, so perhaps I don't understand what you mean exactly, right? But the definition of clusters, like well, points with a high intercluster similarity and a high intra dissimilarity, right? So you want, in that definition, you kind of want what you said, these overlapping things. If I understand you correctly, it's what you would want. However, between those two, and then I'll get to the averages, right? And that's why we would do this or wouldn't do this. Suppose that your data does look weird. I call it snake-like, right? You could have like this but if it looks like this, right? This is basically how your clusters look, right? So suppose that my data actually looks like this, right? Looks like a happy little snake in space, right? Actually, earlier in the lecture, I mean, we had these errors, and I was always talking about bananas in space. I mean, if you would have taken the lecture last year. So bananas in space. We have a banana in space, and now we're going to apply hierarchical clustering with complete linkage. Because if we do single linkage, then it would find the one banana, right? I mean, it would be very happy. But suppose that we now use complete linkage. What would we find? Exactly. So just very short. We would sort of force our algorithm to find convex roundish clusters, and would start to find random blobs, parts of the banana, random bites of the banana, random parts of the snake, and then later combine them, rather than, well, let's build the snake from the head, right? So the results, definitely meanwhile, maybe less meaningful, but also the final result may be completely arbitrary, right? So what I want to illustrate here is that essentially in clustering, let's call it the beliefs of the structure in the data that you think that are live in the data, they matter a lot, because those beliefs that you put in, this is essentially defines what the result you're going to get is going to look like. If you use complete linkage, you're going to find blobs. It's just, you tell the algorithm, find me blobs, right? And and it's going to find you blobs, and you're like, oh my God, I found blobs. Does this mean that the data is truly blobby? No, it might be a snake in space, right? But to discover the snake in space, you need to use single linkage. Now, if you're going to start to use single linkage in blobby data, you're going to find a weird snake, right? So there is not really a perfect answer. So Nahaya asked, why don't we use centroids? We call this group average, group linkage. I mean, there's a number of different names. And group linkage kind of merges, I mean, at a slightly higher cost, merges the benefits of both single and complete linkage, but it at the same time also has a bit of both of the downsides. It is slightly less easy to determine what is it now going to return. So this may be an advantage, it's more versatile. It may be a downside, because yeah, if you know you want snake-like clusters, use single linkage. And if you know that you want to find blobs, use complete linkage. Why would you use something in between? But in the end, what you do, similar to k-means in a way, k-means we have to restart many times because randomization. In a way, hierarchical clustering, yeah, restarted with different measures of distance between clusters and analyze post hoc which ones make most sense, which give you dendrograms or scores. This is like, yeah, this really, then we get very nice compact clusters, right? And these are all questions that are completely exploratory. Beforehand, it's almost impossible to know. In certain cases, like you mentioned earlier, you do know what points or what makes points, what is more important to make points similar than other things, then you can weave it in a little bit. But otherwise, you're just really exploring. Ben? If your data is high dimensional, you're screwed. That's the short answer, or the not quite answer to your question. I think I mentioned last week in this course of dimensionality interlude, right, that not so long ago, and I'm talking like, let's say 10, maybe 15 years, 5 to 10 dimensions was already considered high dimensional. Because the moment you go beyond that, right, we did the example last week between the similarity between you and your neighbor. Yeah, the more meaningless, between quotes, features you have for the similarity measure, the similarities between data points all tend to the same value. It gets dominated by the uninteresting features rather than by the interesting features. So this essentially, so you need a very smart distance measure that can somehow ignore the uninteresting features. But yeah, what is interesting, what is uninteresting? Before you know it, you don't. So there are many very advanced methods that try to crack that nut, but that really goes beyond what we can cover in EML. So for now, let's just apply k-means and friends on reasonably low dimensional data, or if you apply to high dimensional data, pray to the gods of data generation that your features are all equally important, because then it's all fine. Then it's all fine. Yep. Then, so if your data is reasonably dimensional, that's not a technical term, by the way, but what you can then do is a bit similar with k-means, right? In k-means, you just run it multiple times, and you pay special attention to those clusterings with a very low clustering error, right? Or very high within cluster similarity, or what do we define, right? There's different ways. Similarly here, right? We can basically see, okay, which of these methods creates dendrograms which have very compact clusters and then very, well, very large distances between those clusters. That is something like, hey, if we see that's well, with the snake one, we see that it stays very compact, right? So with single or with complete linkage, no, single, I'm not screwing things up. And with complete linkage, we get, yeah, that basically it merges everything only at the end. It's not really structure. Then probably your data looks more snaky than blobby. Yeah? Good. I have still a lot of slides to cover. So, but actually, if I find this interesting. So, k-means, do we find snakes? Do we find blobs? Do we find something else? Does anybody have an idea? Somebody else, maybe? I don't know. I mean, that's who wants to wager? Oh, yeah. Okay, sorry, I didn't see your hand. Maybe both. No, it's one of the two. Blobs. Okay, sorry. Blobs. Yes, blobs. Why blobs? We're trying to find the closest point to the centroid. Yes, correct, correct. You could even pin it down even further. We have this square distances, which is essentially the poor person's approximation to a Gaussian. So k-means really loves finding blobs, respectively Gaussian-shaped clusters. So this also shows that, well, applying k-means, yeah, if your data is not blobby, so to speak, then it may find arbitrary things. Turns out that many data sets are indeed quite blobby, except until you have the one that is not, right? So hence k-means is not the panacea, is not the ultimate method. It just doesn't exist. Good. Okay, yeah, some quick definitions, not very interesting, but perhaps useful. You can compute, of course, now the distances within a cluster, right? We call this the diameter. If you have a very compact cluster, so the maximum distance within a cluster, between points in a cluster, is very small. We call it has a small diameter. That makes it very compact. These are the clusters that are very flat in the bottom in the dendrogram, right? But, small, large, and in between diameters. This is exactly the analysis we just did, right? What is the shape of the cluster that you can find? Yeah, the second part I'm going to skip over. This is just, right now not so important. We spoke about k-means and that we could make it more robust against outliers by going to k-medioids, right? And I kind of told you, okay, k-medioids, in general, you want to avoid it. You could also say, okay, well, wait a second, why don't we go from hierarchical clustering, and rather than having some arbitrary measure between two clusters, right? And that's why don't we also do, especially the average one, why don't we do hierarchical medioids, right? Centroid linkage. Essentially, the short version is friends do not let friends use centroid linkage, because the moment you start to merge clusters, the distances between the now newly formed cluster and the distances that you had before, they can essentially start to flip. So you used to have 2 points that were far away from many other points, or very close, right? And that's, but not as close as they were. And now you merge them, and now you choose one, and then if you choose the, let's say if you choose the one or the other in the first initial step, then all of a sudden you can get a completely different clustering than you would have had if you had chosen the other one. So there is what we call inversion going on. There's a sort of an arbitrariness. That is very badly explained. I apologize. But I don't want to spend too much time on it. Friends do not let friends use centroid linkage. We're not going to ask about it in the exam, hence it's also a bit grayed out, but I didn't want to gray out too much because then you couldn't see it. And that's perhaps a bit too much. Okay, these are the slides that I wanted to have much earlier, but I didn't want to flip through them. We have a data set, 2 variables, right? So it's low dimensional. Let's play agglomerative hierarchical clustering. First iteration, which points are we going to group? Pointing at them, I need to hear it. No, I was talking to him. I was talking to him. That's, which 2 points would you group together? 6 and 1? Okay, does anybody have 2 points that they want to group together even more eagerly? 5 and 7, yeah. Anybody have an even better? No, okay, I'm sorry, 5 and 7 was indeed the correct answer here, but 6 and 1 is also quite close. So I'm going to count it half correct. Good. Next up, 6 and 1. So that's up till now, it didn't really matter how we measured the distances between the clusters, right? That's it kind of did in the second, but that's so now it does start to matter. So what we're doing here is, if I have it correctly, I think this is single linkage. So we use the closest, so the snake, right? That's what would be the next step now? Yes, you. 857. Okay, yeah, so in the example, yeah, that's correct. It's correct. Okay, I'm somehow there's something weird here. 857. Yeah, well, we can play this game for 1, 2, 3, 4, 5, 6 more iterations. Let's not, right? You get the gist. You get the gist, right? But for next year, I'm going to put these slides a bit earlier because getting the intuition before is so useful. Here we have a quick view for if you now do this game on the same data with a different linkage method. And as you can see, you get quite different results. Which one do we like better? Just based on the dendrogram. This is a rhetoric question in this particular case. right? Maybe you like the right one better because you can see like, well, so single linkage, right? Finding snakes. Up. There's clearly something snaky going on here, right? And maybe actually here you like this one better because, well, you can see that here once we start to combine these clusters really at the end, they're far apart, but each of those are, well, quite similarly distant, right? So maybe we like that one better. We don't know. I don't know, right? So somehow we need to evaluate if the clustering is good. I'll say a few words about that in a few minutes. In a few minutes also stop. This is also important. How you choose now your dissimilarity metric, right? So right before we were talking just simply about Euclidean. Makes sense in many cases, but not always. If we look here at this figure, we have three variables, right? Green, pink, yellow. Or should know these are observations, sorry, over the variables, over different variables. Which of these two variables are more similar? If you purely look at Euclidean distance, it is the yellow and the pink one, the ones at the bottom, right? Those are closest. However, does anybody have a case why maybe the yellow and the green one are more similar? Then they're much more correlated. Yeah, correlated. Correlated. Okay, it's almost time to wrap up the lecture. I say correlated, but indeed they have the same shape, right? And that's so. Just looking at the absolute values, just looking at the Euclidean distance is never going to show this, right? No matter what linkage you choose. So even how you define your distance is really important, or even. I think if I would have asked any of you what is the most important ingredient, probably you would have said the distance measure. But determining the correlation between features and using that, that makes a lot of sense as a distance as well. But not always, right? Not always. If they all three are at the bottom and it just means some random wiggling, right? Then the correlation may choose, okay, well, these are now the most similar, and yeah, it's not. There's again not to be said in general. This is better than that. You have to try. You have to see. You have to think about your data. You have to visualize your data. It's hard work. Yeah. Here I'm just going to blaze through the example. I mean, there are examples where this really works. Not so important. You understand? Good. Some practical issues. Should or shouldn't we standardize the data? Can anybody make a case why we should? And then maybe the same person why we shouldn't, or maybe somebody else why we shouldn't. My favorite question with these two things is always like, what could possibly go wrong? Yeah, depends on whether we look at absolute or relative distances. Yes, absolutely. So, whether we care really about the values, right, or not. Indeed. So to then answer in a way my own question. So if we care about it, then we should definitely not standardize because, and if we don't care, then we should, because otherwise, just like in the example I skipped, let's say the number of socks that are being sold will probably greatly outnumber the number of laptops sold, right, depending on which shop you go to, right? I mean, but let's say at Galleria, now that they are insolvent, but they're still open, right? I still think that they will sell more socks than laptops. Yeah, if we care about that, we should choose accordingly. Hardcore clustering, we already saw, which dissimilarity, well, matrix or measure. Actually, I'm going to change this to measure. Matrix doesn't really make so much sense, but of course, the moment I give you a dissimilarity measure, you compute a dissimilarity matrix, and that's essentially what we work on, what we operate on. What type of linkage? We discussed this at length, right? Do you want to find snakes? Do you want to find blobs? Do you find something in between? Yeah, your choice is as good as mine. We need to see. And where do we cut a dendrogram? We also played that game earlier on, so you're experts. For k-means clustering, how do we set k? I showed you the elbow method, right? And there are different ways of approaching this that are more advanced. It is a bit of a black arts, what is it, black magic, what do you call this? I mean, it's an art, it's an art. Validating the clusters. I would need, at the very least, a complete lecture. So hence, I'm going to do here what all machine learners do. We're going to ask the expert. So essentially, this means I have no damn clue. I do, but not right now, right? I don't have the time. So this is also what you always see. This is why I want to explain this shortly. A user-determined or a hyperparameter in an algorithm, in many machine learning papers or studies, okay, well, the expert can set this value. This is machine learning speak for we have no damn clue, right? It's like if you want it high or low, like, okay, you go ahead, right? But the problem there is that essentially no expert, or at least no expert I've ever met, and I speak to many domain experts, has any clue how to set these things. The first thing they will ask back is like, no, it's your method, you decide how should I know how many clusters are in the data? That's why I ask you, you're the expert here, right? So there's a bit of a discrepancy there between, well, the machine learners who, like, I don't want to answer this question, and those are exactly the questions that the domain experts want us to answer. So maybe in the final lecture, in EML, I will go a little bit deeper into this entire conundrum of how to evaluate, especially exploratory methods. For supervised methods, it's reasonably straightforward. You know how, right? Estimate test error. And if you have a higher accuracy, it's better, except when it's not, right? If the differences are too small. If we have labels, this is a sentence, I mean, I have to say it out loud. You also find it in the book in some form or another, and people will tell it to you. It's difficult for me to pronounce these words. If we have labels for at least some observations, we can assess class purity. Well, okay, thank God that I wrote at least some observations. Oftentimes, you see people evaluating clustering methods with labels for all of the points that they already had. This does not make any sense. Why not? So essentially what we're then interested in, right? We have labels, and we're going to do clustering, and now we're going to compute per cluster, essentially what is the accuracy per cluster. So we have, did we indeed cluster the green points and the blue points, the red points completely the right way, right? So this is the red cluster, this is the blue, this is the green. Doesn't make sense. Exactly. That's the first one. If we have labels, why would we cluster, right? And that there is a more subtle issue. There's a more subtle issue. And maybe? Yes, the labels are excluded before clustering, yes. Now, otherwise it would, otherwise it's just a bad experiment. I mean, plenty of people will do it that way, but that would be a really stupid idea. Does the cluster structure in the data necessarily and exclusively have to be correlated with the labels? Other way phrased, might it be that the data admits a very sensible clustering that doesn't have anything to do with the label assignment? Yes, of course, of course. And there might be many different clusterings, right? There is not necessarily one exclusive clustering. So now suppose that your method found a very sensible clustering, but it gets a very low score on these few samples that are labeled. Oh my God, you have such a bad clustering. No, no, absolutely not. Clustering is inherently exploratory. It is not supervised. It's not trying to predict as well as possible. So this evaluation only makes sense if there's one type of structure in your data, and that is the one correlated with the labels. This never happens in practice. I've never seen it before. Yeah, well, bootstrap, you can always apply bootstrap. I mean, just like cross-validation in a way. But, yeah, okay, I'm going to skip this. I mean, this is really nice. I was not even aware that I included this. That's a bit of a leftover. This might show up in the final lecture again. Back to the very first slide. We now spoke exclusively about exclusive clustering. Every point is assigned to only one cluster and one cluster only. You can imagine that if we allow to be part of multiple clusters, right, or any of you, of course, right, I'm not going to be exclusive there either, that opens up, well, so many more possibilities for probabilities, right? I mean, that literally probabilities, like we can now try to maximize the likelihood of the data under the cluster assignment. So what is the probability of the cluster generating the use versus the use, right? And we want to maximize this. That's a very probabilistic notion. raises questions, okay, how on earth do we compute likelihoods? What are the distributions? Do we want to fit Gaussians, multivariate Gaussian? Do we want to do it non-parametrically? How do we do this efficiently? And so on and so forth. All questions that people are still very actively looking into. So a few weeks ago, the first lecture when I took over, the online one, right, or the pre-recorded one, I was at NeurIPS in New Orleans, one of the major machine learning conferences. I was with a number of my students. They were amazed with how many papers, new results there were on clustering. Like, yeah, I'm not amazed anymore because I know that it's a very important problem, and B, it is very hairy, it's very difficult. Right? So, of course, we are still developing very much from different angles. Beating k-means is still an issue for all those new papers. These are more solutions for niche problems rather than in general. K-means plus is your go-to method. I'm going to wrap up with the final sentence here. Be cautious and thoughtful when you cluster data. Let me rephrase this slightly. Be cautious and thoughtful whenever you deal with data. Regardless of whether you're doing machine learning, predictive, unsupervised, be very careful with what you get. Right? Data is very slippery, and it doesn't necessarily lie, but the results that you may get may be completely nonsensical, right? So always verify your results, always look into, does it make sense for me, for my application? And that's going to be my segue to wrapping up this lecture. And then I tell you, the summary you can read yourself, that there's no thank you slide. I'm just going to say thank you very much for your attention, and see you again next week. We're going to be talking about trees and forests.